This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. So we discussed about common mode gain, then common mode to differential conversion in the last lecture. And then I thought I will continue, but based on some of your questions, I think I will show you using some simple equations how can we understand the concept. So I'll be going through the common mode gain and common mode to differential mode conversion using some simple equations and diagrams. So in summary, you have no options. Means you have to study, you have to understand. So that's the reason I'm again going through this section. So I was thinking yesterday how to present it in a much better way because I don't have time, so I have to come up with some strategies. I think the strategy that I came up might be a good way of explaining the concepts, how the common mode signal will become in the differential signal, because that is one confusion. The common mode gain is easy to understand. You got some common mode signal in the input and then that is appearing in the common mode output. But then a little bit confusion is how this common mode signal will appear in the differential mode, because that's what we have to understand logically, because understanding logically is very important to lay down the foundation. So then what I did is I have got a couple of printouts and then we will write down some equations, simple equations. So this is an ideal current source and I am going to set this ideal current source as 4 milliamps. So ideal current source. So input is something like this. I'm going to vary like this. So input is like this. So this is my V in 1, this is my V in 2, and then this is IC1, this is IC2. So this is common mode signal. So this is common mode. So common mode signal. So this is a common mode signal because I am connecting here one signal that is increasing, that is delta V. And then here also same time delta V is increasing. Then because this is 4 milliamps, so your IC1 plus IC2 should be equal to 4 milliamps, which is equal to IW, because this is an ideal current source. Ideal current source will make sure that your current is always at IW, that is equal to 4 milliamps. Then when you connect this delta V, actually what is happening is then your collector current should increase. IC1 will become IC1 plus delta V, because IC1, when you don't have this delta V, you got IC1. Why do you are getting IC1? Because we provide a bias, DC bias. So that is the reason IC1 is flowing, IC2 is flowing, and then you biased this differential amplifier properly, and then you also connected this current source. This current source will make sure that this is 4 milliamps. And then you provide a bias here, and then IC1, IC2. So when delta V is varying, it will become IC1 plus delta V. So here also will become IC2 plus delta V. But the problem is, your current cannot exceed 4 milliamps. So IC1 plus IC2 plus 2 delta V will not be equal to 4 milliamps. You know the problem? So you can't have, so here if you got a common mode signal, this may be a noise. This could be a noise. So when you have common mode signal, the problem is you are trying to increase the collector current. Here IC delta V, IC2 plus delta V same time, but then this collector current cannot increase because IC1 plus IC2 should be equal to 4 milliamps. When you are then this is a delta IC. So delta IC, so this is also delta IC, because then delta V is changing, your current is increased by delta IC. Current is increased by delta IC. So when current is increased by delta IC, so what you are trying to do is IC1 plus delta IC1. So that is this current. And then here it is plus IC2 plus delta IC2, which is equal to 4 milliamps, which will not be equal to 4 milliamps. You know what I meant? Because IC1 plus IC2 should be equal to 4 milliamps. When you are putting delta V here increment, then here delta V will contribute to delta IC1. So you are adding on the top of IC1, this delta IC1. So IC1 plus delta IC1. Same happens here, but that is not possible because it should be 4 milliamps. So that is the reason, if you got an ideal current source, then your common mode gain equal to how much? 0. So that is the reason this may be a noise, this may be a noise. If you got ideal current source, then you don't have any problem because you don't get any fluctuation here. This IC still it is clean. Now what we are going to do is, so that is a common mode signal. Now I am going to look at the differential amplifier. So I am going to, differential. So differential signal. So differential signal means here I am connecting delta V, here also I am connecting delta V but inverted. And then this is a V in 1, this is a V in 2, and then this is IC1, this is IC2. And then when you have delta V here, then what will happen to, so again this is 4 milliamps. Then IC1 plus IC2 equal to 4 milliamps. Then here what is happening is you are increasing delta V, so here the current will become IC1 plus delta IC1. So what will become IC2? IC2 will become IC2 minus delta IC1. So in that case it is fine because IC1 plus delta IC1 plus IC2 minus delta IC2, which is equal to 4 milliamps. And then if this delta V's are same, so then IC1 and IC2 both are same, so that will cancel out because this is delta V1 or delta V2, both have got same amplitude. So delta IC1 equal to delta IC2. So it will cancel out and then you are getting, so here when you apply differential signal, then what is happening is you can get amplification here. Why? Because here when you are connecting a signal, then here you definitely the collector current will vary. When you are connecting an inverted signal, you get amplification here, and then even differential signal you can get it. Why? Because you are connecting a differential input signal. You know what I meant? Because here you will increase the current, here you will decrease the current, so sum of the current equal to 4 milliamps. Now we got to, so into this case, now what I am going to do is I am going to add a common mode signal. So that is my noise. So this is your signal. Now this is my noise. Plus this is a noise. The signal is kind of a triangular, so that is my output, new output. So then this is a noise, and then this is a signal. Again, this is a signal, this is a noise. So if that is the case, what will happen? Because you got the input here, and then, so when you add up these two, maybe it will look like this. Some noise, because this is only part of the noise I have drawn. Here also, when you add up, it will look like this. Input. Now what I am going to do is I am going to measure, this is Vx, this is Vy, this point. So I am going to measure Vx with respect to this ground. So how will my waveform look like? So Vx, when I am measuring, obviously you can say that this will be inverted. Yes, the signal will be inverted with a gain here. But then whether you will see the noise. Because that is a common mode signal. Will it appear on this one? Somebody said it will occur, so I am going to write down the equation. So here you got delta V, so here it is delta V and noise. So here it is delta V and noise. So then what is the equation here? So with signal plus noise, what is IC, total current here? IC1 plus, what is the equation? So delta IC1, that is due to your signal. Then plus delta IC, that is noise. So that is the current, total current now here. Then what is the total current here? So that is equal to IC2 plus delta IC2 or plus or minus. Yeah, so this is minus because it's a differential signal. Then plus delta ICN. And then when you add up these two, you should get 4 milliamps. Then IC1 plus IC2, this will anyway will cancel out because your delta IC1 equal to delta IC1 equal to delta IC2. But then these two can't be here because then when you add up these two, you won't get 4 milliamps. You know what I meant? Because of means, then what is the meaning? So there won't be any noise because how can this noise be present? If this noise is present, then what will happen is your current will not add up to 4 milliamps.
The source we use won't be ideal.
No, here it is ideal. So this is ideal. Definitely we are talking about ideal. So this current source is ideal. Then what will happen is this is a bias, this is a DC current plus delta IC1 due to this signal, then plus noise, your delta ICN increment here. Then here you got inverted signal, IC2, your DC bias current minus delta IC2 because this signal is inverted, so that collector current will decrease, and then plus this is a common mode noise delta ICN. Then when you add up these two, this will cancel out, and then IC1 plus IC2, that is 4 milliamps. But then you can't have delta ICN 2 times delta ICN here because this is an ideal current source. So because of that you get a clean signal here. Again here Vy with respect to ground, again you get a clean signal like this. Vx minus Vy, that will be a clean signal. You know what I meant? So that is the reason if you got ideal current source, then you can't increase the current in both the arms because the current is already set by 4 milliamps. Now when you have a non-ideal current source, then the problem starts. When you have non-ideal current source, what will happen is what you are trying to do is you are here, this is your signal, then plus this is your noise. Again, this is your signal, this is your noise. And then this delta V, this is a delta V N, maybe I'll call delta V, maybe signal. So delta V signal, delta V noise. And then these are the inputs that is going here, here one and then here. Then what will happen is if you got a resistor here, that is your current source is no more ideal, the impedance equal to RW. In that case what will happen is your initial current is IC1, initial current is IC2, and then IC1 plus IC2, that is equal to 4 milliamps. We set this as 4 milliamps. So a non-ideal current source. So when you have non-ideal current source, now the problem starts. So now what will happen is you got IC1 and then when you have signal like this, so what will be your the total current here? IC1 minus, because this is a negative. So negative ICG, because that is your signal. That is the reason I put G. And then plus delta IN, that is the total current here. What is the total current here? That is equal to IC2 plus delta ICG plus delta IN. But then the question is when the noise is increasing here, that is a common mode, and then I said that will appear here. This point, the voltage will be increasing. You know what I meant? And then when this is not ideal, what will happen is this current will come here, that current will come here, and then this current will come here. And then what will happen is this both will be adding up. Then what you will get is IC1 plus IC2 plus 2 times delta IN. So that is a current here. Okay, so then you got 4 milliamps, that is your IC1 plus IC2. So then plus 2 times delta IN also is coming. If it is ideal, what will happen is this 2 will come here, but then this current source will not allow, this will not flow, only this 4 milliamps. But if it is non-ideal, what will happen is this 2 delta IN will flow through this resistor. See, 2 delta IN. Then what you are trying to do is you increase your total emitter current. So when you are increasing your total emitter current, what will happen to your collector current? Collector current also will increase. So then here 2 times delta IN means here already that current is increased. And then what will happen is this collector current will increase, this collector current will increase. Means your noise is coupling little bit here. So then what will happen is you measure Vx. So when you measure Vx with respect to ground, and then this signal is equivalent of maybe like this. Little bit noise, because this is only one noise I have shown, and then here this is equivalent of something like this. When you measure Vx with respect to ground, then what will happen is you get some noise here in your amplified signal. Again, Vy with respect to ground, you will see some noise. And then because you got a common mode signal at the output, we call it as a common mode gain. So that is the reason we defined a term called common mode gain. So common mode gain, so this is a common mode gain, because now we got a gain for the common mode signal. So did you understand? Yeah, so that is the reason. But then how about Vx minus Vy? Yeah, that will be clean. Why? Because the noise in both the places anyway will cancel out in the Vx minus Vy. So your differential signal is still clean, but your single-ended signal, we are measuring this point Vx with respect to ground, got some noise coupled. This noise coupled because the remaining current is fluctuating here, so you increase the current greater than 4 milliamps, that increased collector current a little bit here and here. So that's how the noise is coupling. Now you can understand, imagine how the noise is coupling. And then, now still we are happy. Why? Because then you will say, I will take current voltage between Vx and Vy. I will be taking these 2 points. Then my signal is clean. But when you have this situation, then you solved this issue. And then you said, now we can make the chip. The input of the differential amplifier, you are going to design a chip. And then when you design a chip with a current source that is not ideal, REE, what will happen is, now our assumption is Q1 equal to Q2, RC equal to RC in both side resistors. But when you fabricate, you can't exactly match it. Whatever the technology you use, there will be very slight mismatch between the components. And then say this RC became delta R. There is a small difference between this RC, which is quite common in fabrication. Very, very small tolerance, not a big one. Not like 10 kilo ohm, another one is 5 kilo ohm, maybe 10 kilo ohm plus 0.001. Slight mismatch. When that comes, the complication arises. Now we are going to connect, you see, this is a signal, and then that is a signal. Delta VG, delta VG. Then you got noise. Delta Vn, so this is a noise. Delta Vn. And then this together, it will look like something like this. Input. So this together, it will look like something like this. Okay. Then, now we are going to connect here. Then what will happen? When you connect it here, initially IC1 is flowing, then here IC2 is flowing. Now what will happen is, what will happen to this current? Your current will become IC1 plus previous case, delta ICN, that is a noise, minus delta ICG. So that is a current here. And then our assumption is collector current equal to emitter current. Then current here, that is equal to IC2 plus delta ICN plus delta ICG. So that is the current here. Now we are going to find out, now we know that when you measure this point with respect to ground, we got the noise. This point with respect to ground, we got the noise. But Vx minus Vy in the previous case, the Vx minus Vy here, it was clean. Now we are going to find out Vx minus Vy. So what is the value of Vx? VCC minus total current, IC, RC, and then what is the IC in your case? This is the value. So then which is equal to VCC minus, so if you put IC1 plus delta ICN minus delta ICG into RC. So Vy, VCC minus this value, IC2 plus delta ICN plus delta ICG into RC. So when you take Vx minus Vy, what will happen? So VCC anyway will cancel out. Then what will happen? So, sorry, RC plus delta Rs, because I forgot that one. So now Vx equal to VCC minus IC1, your DC bias, delta ICN minus delta ICG into RC. Vy, VCC minus delta IC2, delta ICN plus delta ICG into RC plus delta R. But then what will happen is when you take Vx minus Vy, this term will cancel out. RC into delta IC1, when IC1 equal to IC2, in that case what will happen is because your bias currents are same, and then what will happen is this delta IC1 into RC, RC into delta RC2 will cancel out. Then what will cancel out? This signal, this one will cancel out with this one, but then the delta R component will not cancel out. You know what I meant? So now what will happen is you are getting IC2 into delta R, then plus delta ICN into delta R plus delta ICG into delta R. See, this is the component, it will be staying there because of this delta R. And then when this component is staying there, you can see this is due to the signal. So this will become delta, so this will become 2 times. Yep. So this is due to the signal, your differential signal. And then this is what is due to, this one is due to the noise. This one is a DC part. You know what I meant? And then we can maybe combine these two because both are DC part. So then what it says is in the equation Vx minus Vy, we should get only this value. Because in the previous case, when we derive, so for the differential signal, we already derived it. So for the differential signal, what will happen is, see, you are getting here Vx minus Vy, when you take it, that is 2 times delta IN into RC. But then here what is happening is, you are getting this delta R, because of that you are getting this extra term in the differential signal. Only expected is this one, but then you are getting this value. So this is arising because of the common mode signal. So now what is happening is your Vx minus Vy, when you measure between this point and this point, then you will get your signal, but then it will be maybe a little bit noise will be there in the differential signal as well. You know what I meant? So because of this term, see, the common mode signal is appearing in the differential signal. So that is called common mode to differential mode conversion. So this is called, so you got a common mode to differential mode. So common mode to differential mode conversion. See, means what is happening is your common mode signal is appearing in the differential mode. So that's the reason we call it as common mode to differential mode conversion. And then all these things happened because of the non-ideal nature of the current source, this one. And then now your differential signal also is slightly corrupted. And then here then you are the chip designer. Then what step you will take? Yeah, so this fabrication symmetry is very difficult to control. Then one way to solve this problem is to make this RE as big as possible. Then when you make operation amplifier, you should be telling the user what is the noise, because that will prevent the application. You cannot simply design some operation amplifier and then use a differential input and then sell it. You have to tell the user what is the value. And then for that, people came up with an idea called how to define it. They called it as CMMR, common mode rejection ratio. Means when you have a differential amplifier, you already got a differential gain. You know what I meant? Your differential gain divided by this common mode to differential mode gain. So they call it as a CMRR. So ideally CMRR means you don't want this CM to DM conversion. Because if you can make this 0, then your differential signal is clean. If it is not 0, your differential signal got a slight noise. So this ratio, ideally, then what is the ratio? Your CMMR, ideally you want infinity. Yep.
Didn't we say it's AD over CM?
Sorry?
Didn't we say it was AD over CM, not ACM minus DM?
No. So AD means the differential gain. Yeah. ACM DM. That is a common mode, real CMRR. So because different definitions are there, so this is exactly what is mentioned in the data sheet in the differential amplifier. I can show you. So that is the reason we call it as, I'll show you the so we write it. Yeah, so we write it CMRRDM. You know what I meant? So that means a differential, because this is a quantity that we are interested. Because this will give you the exact realistic picture of how much noise will be there in the differential signal. So that is the reason we defined this term, and in the op-amp we will be using this as a standard. So that is the reason we discussed CMRR. Now you know, using simple equations you can find out these things and you can understand. Now we will go back to our slide, and then that's the reason here you can say high CMRR around 100 dB minimum. That is a minimum value they can guarantee. So that in your application, if you are amplifying a very small signal contaminated with noise, you need a high CMRR operation amplifier, or you should have the amplification. So CMRR defines the ratio of wanted amplified differential input signal to unwanted converted input common mode noise that appears at the output. And then
How do you compute the gain, sir? ACM hyphen DM. How do you compute that?
so that we can firstly we can measure it. Yeah, we can calculate it, we can measure it. So in the op-amp they usually measure it.
How will be like common mode in differential? So you're operating in differential mode. So you know differential mode gain. How do you find out the common mode gain in the differential mode? That's what I'm
No. So common mode means you connect maybe some common mode noise.
Yes, sir.
And then you see that how much it will come in the differential signal.
Okay, sir.
Yeah. So you know what I meant? Yeah.
The gain in common mode itself.
Yeah. Then you find out what is you connect a non-noise in the input and then measure the output. Then that we can find out.
But in your lab, why we use only one set without divided by the VCM, but not the difference?
Which one, sir?
In the laboratory, that we did this week. We're going to find any
No. So in the lab we have two types of CMRR. So one is simple CMRR, that is equal to AD by ACM. Then another one is CMRR DM. So that is called AD by ACM DM. Yeah, why? Because we have shown these two, because in some places they use AD by ACM, but then in some places there is a CMRR DM, they have used AD by ACM DM. But most of the op-amps, what they meant is the CMRR DM. Yeah, that's the reason we are using both. Yep, then we came up to here and then so we already calculated ACM DM. See, already you asked me how to calculate it. That is equal to delta RD. If you know how much is the tolerance, divided by 1 by transconductance plus 2 RE can give you the value, actually, theoretical value. But then in the op-amp, most of the time what they do is they do conduct and experimentally they measure it. And then this is a equation that we derived. Then in order to realize a current source, and current source with a high impedance, you will be using something like this. You know what I meant? We will be not using a simple transistor. Instead of that, we will be using an emitter degenerated one. Because then only you get very high impedance for the current source. And then, because your R out will be very big value. So that when you design, you will be designing something like that. Even for R1, we can use another transistor. That is a cascode. When you realistically design it. Then, when you put this one, then what change we will have here? Delta RD is same, 1 by GM is same, then your RW. RW now will become R out 3. So what will be the R out 3? You can, now ACM DM will become 2 times R out 3, because when you look down from here, you see RSS. Now you look down, you get R out 3. Then you can substitute the value of R out 3 equal to 1 plus GM3 R1 parallel R pi 3 R out 3 plus R1 parallel R pi 3 from this equation, which we already know. And then you get ACM DM equal to delta RC by 1 by GM1 plus 2 times C, because this RW is kind of a course. We don't know what is the value of RW. So when you realistically design, this is a value. Because you will be connecting another transistor here. Then, so now we know that about the differential amplifier. Now, there is one more thing with operation amplifier. So when you have operation amplifier, you might have noticed in most of the operation amplifier, you have got 2 input. And then you got positive, negative, you got only 1 output. So you got only 1 output. You know what I meant? In the operation amplifier, there are some operation amplifiers that got differential output. So that is called differential input, differential output. But most of the operation amplifier, they got only 1 output. Secondly, when you design an operation amplifier, your first stage is a differential amplifier. For the differential amplifier, in order to get very good noise rejection, how you will take the output? You will be taking Vx and Vy. You know, Vx minus Vy you will be taking. Means in this differential amplifier, maybe I will draw using another. Yeah. So this is a differential amplifier you have designed. You have designed this differential amplifier. And then your current source, this is not ideal, RW. This is also a slight variation because it's a realistic case. Then, this is the input of your operation amplifier. So I'm going to draw the operation amplifier here, and then this is a big operation amplifier. So this is your operation amplifier, and then this is a 1 input, and then this I will take it out. This is another one. So this is a inverting or non-inverting. So this you got any 2, and then you will be taking Vy, and then you will taking Vx. You know what I meant? Vx and then Vy. So you will be taking Vx minus Vy, because then only you get a very good output, clean signal. But you get Vx minus Vy. In the operation amplifier, you are not taking this output. Here you may have another amplifier, a simple amplifier, to further amplify the signal. Or you got some other filter. But then this output is like this. Now my question is, and then maybe here also maybe somebody connect a current source, then this is a common emitter amplifier. How will you connect this signal to here?
You can ground your device.
So if you ground this Vy, then you are grounding this transistor collector. And then if you take Vx, then what is the use of a differential amplifier?
We can use 2 supplies, sir. Positive supply, negative supply. By that our this thing, VB2 won't be compromised.
No. So then this is a VB. How will I connect this to here? Because you got Vx, I have to connect Vx minus Vy. That is a differential output. If you connect Vx alone, then what is happening is you don't need the differential amplifier. You are not making use of the features of the differential amplifier. If you connect Vy alone, then you connect your ground, this ground with this ground, then you don't have the effect of differential amplifier. You know what I meant? Then how will you connect this to one single-ended? Because you are taking your signal not with respect to ground. Your signal you are taking this one with respect to this, or this one with respect to this one.
Then give it across base and emitter.
Base and emitter. But then what is happening is you are shorting this one. Because you need Vx minus Vy. Because if you don't get Vx minus Vy, then you are caught. Then you can say that I am going to design a differential output amplifier. Yeah, some amplifier designs are there, differential output. But then what will happen inside the op amp, you got multiple stages of amplification. Then everywhere you have to use differential amplifier. But then this became a problem in the design. Then people came up with an idea. They can convert this two into a single line. But that single line got all the properties of differential amplifier. Yeah, so that's what we are going to study. And then, so how people can do that one. Then people thought about it and they came up with a design. With that design, it's very interesting. They get the Vx minus Vy property only from one line. So that is easy to connect to next stage. And then you can connect to that next stage, but then you have to design, how to design then, you have to modify the design of the differential amplifier. So how they have done, so that's what we are going to study. So then you can see that this is a, if you are doing like this, if you are taking only one output, then not very good. You are not getting the effect of differential amplification in the operation amplifier. Then single-ended output, supply noise corruption. So if you are taking only one, what will happen is IW by 2. So this is IW, then this is IW by 2 plus delta I, and then this will become IW by 2 minus delta I if you are connecting a differential signal. Then if you are taking only single-ended output, what happens is the most critical drawbacks of this topology is supply noise corruption. So you don't get the effect of differential amplifier because you are taking only one output like Vx or Vy. So these are single-ended. So that is not good. Then better alternative is this one. So what they did is they designed, instead of a load, they designed a, what is this one? Yeah, current mirror. So when you design a current mirror, you can get some good effect, means you can convert the two lines into one line. So then the current mirror, if this current is IW by 2 plus delta I, this current also will be IW plus delta I, because that is a current mirror. This topology performs differential to single-ended conversion with no loss of gain. With current mirror used as a load, signal current produced by Q1 can be replicated onto Q4. This type of load is different from the conventional static load and is known as active load. So this, now we are using active load, but then this can convert your double Vx minus Vy, that effect differential output into single-ended without losing the properties of the differential output. Then how can I prove it? So how can I prove is, now I am going to connect here. What I am going to connect here? Single differential, so I am going to connect a differential signal. So here delta V step is increasing, and then here delta V step is decreasing. You know, differential signal I have connected. So when I connect this differential signal, what will happen? So what is the current here? So if it is IW, then this current will be IW by 2, and then this current will be IW by 2. So this is IW by 2 plus delta I. Then what is the current here?
IW by 2 plus delta I and the current drop by Q2.
No. Here, my question is this point, what is the current?
There's no curse
Oh, sorry, I think, my mistake. Yeah, so this point, when you got a delta V step, yep, then you got IW by 2 plus delta I. Now my question is, if this is IW by 2 plus delta I, then here it is a step down because it's a differential signal. So what is the current here? Minus. And then what about this point?
The sum of those two currents, because there are two loads.
No. This is a current mirror. If here IW by 2 plus delta I, what is the current here? Yeah, plus delta I. So then IW minus 2 delta I, then here IW plus delta I, then what is the current coming here? Yeah, 2 times. Then that is I1, I2, this is I3. So then I3 equal to I1 minus I2. So that is equal to 2 times delta I. So then the voltage here is 2 delta I into RL. That is the differential output we get, Vx minus Vy. So for the differential signal, then we are not using even amplification, not losing the amplitude as well. Then you are getting the effect. Then if I were you, then I will ask, how about a common mode signal? Can I prove that a common mode signal is rejected? So that's what we are going to show next. So V out equal to 2 times delta into RL. One output gives same result as differential output for differential input signal. The input differential pair decreases a current drawn from RL by delta I, and then active load pushes an extra delta I into RL by current mirror action. These effects enhance each other. See, that's what I have shown. Now, what we are going to do is a common mode signal, because that is our interest. When you connect a common mode signal, then if this is, so now we are assuming this ideal, and then, so if it is a common mode signal, then if it is a differential output, you should not get a common mode signal here. And then here it is IW by 2 plus delta I. Now my question is, what is the current here? Yep. Then what is the current here? Yeah, because it's a current mirror. So then what is the current here? Yep. See, you don't have anything. So that way you can understand. So this one, so now the common mode is rejected. So one output gives same result as the differential output for common mode input signals. So pretty much like this. So active load versus static load. The differential pair with active load is also known as 5 transistor OTA, where OTA stands for operational transconductance amplifier, and was used to refer CMOS op amps in olden days. So that's what you do in the lab 9 if you are doing the bonus. OTA, operational transconductance. In the olden days, people used operational transconductance amplifier. That's a current amplifier. And then that is the reason in the lab we are doing OTA with this active current load. Now you know why we are doing. The load on the left responds to the input signal and enhances the single-ended output, where the load on the right does not. But then the only problem with this design is, again, MOS. MOS also, similar to bipolar counterpart, MOS differential pair can also use active load to enhance single-ended output. So whatever we discussed so far is equally applicable to MOS transistors. But then, now there is a problem. If we want to find out differential gain for this circuit, then the problem is the circuit is symmetric or not. So whether it is perfectly symmetric or not. It is not. Why? Because these two transistors may be identical, but then here you see N, this point is connected here. It's kind of a diode connected. But here, this is different. When you look from here up, you see R of 4. But when you look from here, you don't see R of 4. Yeah, so this is not symmetric. So how will you find out then differential gain? The only way to find out is, so this is 1 by Gm parallel R of P. R of P means the P and PMOS. So that's the reason when you look up, and then here it is R of P. And then delta Vp not equal to 0 because it is not symmetric. The existence of signal paths in differential to single-ended converter circuit suggests that the voltage gain of the circuit must be greater than that of a differential topology. Means then you solved one issue, but the analysis becomes now complex. But then the only way to do is, because of the vastly different resistance magnitude at the drain of M1 and M2, the voltage sinks at these nodes are different, and therefore node P cannot be viewed as a virtual ground, because if you got asymmetry, this point will not be virtual ground. Then what you will do? Go back to our old technique. Draw the full small signal and then derive the expression. So we can't do any other things because we can't split it. And then again this part you don't have to study for the exam, this small signal for this one. This is only for your understanding. Only this part. Please don't misunderstand. Only this part, this one. I will not ask for the exam to find out maybe something from this diagram. And then this one I just included to show that, so because anyway this is very good design. Here you can get the effect of 2 lines, differential output in a single line, but the only problem is then the finding out differential gain is difficult because it is asymmetric. Then the only way to tackle is you draw the full small signal and then you can get the gain. So when you draw the full small signal, then what is happening is see V in 1, then this part is open, then the current source is open, and then you got this part V in. So this is the source, and then here it is open between gate and source. Then you got the current source between source and the drain here, and then this current source here. Then you got RO1, RON because NPN. So this is NMOS, and then this is also NMOS. So that is the reason RON. Then when you look up, you are seeing ROP parallel 1 by GM. That we already said from when you look up. So here when you look up, then you see ROP, and then you also see a current source, and then this part is grounded. And then you can write down the equations. So at P, Ix plus Iy should be equal to 0 because this is the Ix current is coming, splitting here into 2. Again here Ix will come. Iy splitting here, Iy will come. So that equal to 0 here. Then you can write down this Va. This is equal to minus Ix into 1 by Gm parallel Ro. Because if this Ix is coming, when you measure this voltage with respect to ground, then what is the voltage? Because Ix, this part is open, so the Ix only can come from here. So then this Va will be minus of Ix into 1 by GMP parallel ROP. And the same way you can write Iy. So Iy equal to V out by ROP. See V out by ROP because this voltage is V out. Plus GMP into Va. So there is a GMP into Va. P is the PMOS. And then Va. Va is this voltage. Then you can substitute because you already got what is Va here. So when you substitute, you can get this one, and then you can rearrange and find out Ix. And then you already got Ix, then we can find out Va, because Va equal to, what is the value here? So when you measure Va equal to Ix into this resistance. So that's the reason this resistance into value of Ix. And then we can find out Va. So what is Va? Va equal to this voltage. So you can apply the Kirchhoff's law. So when you apply Kirchhoff's law, Va equal to Ix minus Gmn into V1. So here into RON, this voltage, because this Vn KVL. Then minus Iy, because here it is coming, Iy minus Gm n V2 into RON plus V out. So that is because this is a branch, and then we can rearrange and make it 0. And then V1 minus V2, which is equal to V in 1 minus V in 2. And then Ix equal to minus Iy, because Ix should be equal to minus Iy. Because V1 minus V2 equal to V in 1 minus V in 2. So then we can rearrange here V in 1 minus V in 2, that is equal to V1 minus V2, and then Ix equal to minus Iy. So then this will simplify. And then you can rearrange and then substitute the value of Ix, because Ix is this value. So it's a bit complicated derivation, and then that is Va, and then that is Ix, because Va we already got it here, Ix we already got it here. And then you can get gain. V out divided by V in 1 minus V in 2, that is equal to Gmn RON into this big value. So this we can simplify as V out by V in 1 minus V in 2 equal to Gmn into RON parallel ROP. So that is the equation. So you don't have to study this derivation. I have just shown you, and it will not be asked for the exam, just for your knowledge. What this shows is your gain, which is equal to Gmn, transconductance of the n-type NMOS into RON parallel ROP. So that is the equation. Means when there is an asymmetry, so from here what you have to understand is when there is an asymmetry in the circuit, then you have to draw the entire small signal. No, because we can't split it. Asymmetry. Then we have to write down the entire equations, and then we have to find out. And so this derivation I will not ask for the exam, or this is just for your understanding. So then what we have studied in the differential amplifier is, I think that is the end of the differential amplifier. And then gain is independent of GMP and equal to that of fully differential circuit. So what it shows is when we derive these equations, actually this gain is somewhat equal to splitting the transistors, somewhat equal. So the asymmetry is not creating much difference. And then, but this is independent of GMP because PMOS is not affecting in the gain. and that is a fully differential circuit. So it is somewhat equal to the splitting the circuit and finding out. But when there is an asymmetry, we can't split it. But then using this equation, we can still say that it is almost maybe same, because the result what we have got is under approximation, because here you can see GMN RON, then ROP, then we are neglecting all these terms because all are small. Then we can approximately maybe, then what it says is even though you got an asymmetry, still we can split it. If it is a small asymmetry, you can split it and then write down the equation. That will be approximately equal to this big equation that you get from your small signal. So two things. When there is an asymmetry, the splitting is not very accurate. So we have to write down the entire small signal and then find out the gain. That is a more accurate way. But then if the asymmetry is not very big, you can split it and find out, then you will be getting an equation which is close to that you write down the full small signal equation. And because then you will be getting this extra term, and then this is very, very small, and then you can get this one. So approximately it is correct. So in the differential amplifier, we studied common mode gain, important concepts, common mode to differential gain, CMRR, common mode rejection ratio, then differential mode to single-ended conversion. So these are the sections we covered in the differential amplifier. And so in my next lecture is about some problems and semester test and then output stages, not examinable. Then in the next in our lecture, that is on Thursday, I will start frequency response. Then there will be one or two, maybe two lectures on frequency response and then one lecture on feedback. That's all for the examinable. Then my remaining two lectures, I will be using the extra lectures, one today to cover some problems today, going through the mid-semester test, and then teaching you some output stages, not examinable. Then again, I got one more lecture, extra lecture, that I will be talking about voltage level shifters, and then how to couple, these stages, different stages, and make an operation amplifier. Okay, so again, that is not examinable. Very good question. I have to check. I think it's the right theater. Yeah, I'll come out and then our lecture. Yeah, we'll come out and talk. Yep.
So, does this does these lectures have the same timetable with the normal lectures?
No, this extra lecture, this is only for this week.